We're taking a look at electric fields, having just finished up the whole section on charge. Now we're going to take a look, okay, what can we now do with these charges? So charges are going to produce an electric field. We'll take a look at a few problems to do that. So from your notes and from your book, we have some formulas that we're going to need. The force inside of an electric field, and I'll make it a vector, although we could do it just with magnitude, but force again has a magnitude and a direction, is equal to the charge, Q, times the electric field. Okay, so here's our first example problem. Actually, before I get into that, let me put up the other formula that we'll need for this, and that is the electric field is going to equal K Q over R squared, because the charge experiences a smaller force as it gets further away from the source of the electric field. Okay, so anyways, an electric field produces a uniform field of strength 4.6 times 10 to the fourth newtons per coulomb, and points in the positive x-axis. Find the direction and magnitude of the force it applies on each charge brought within it. So we have three charges here as examples. So we're going to need this first formula, F equals QE, and we want to know the force. So the force is going to equal our Q is in microcoulombs, so we do need to change that to coulombs. So I'll go ahead and do that, times 10 to the negative 6 coulomb. And our field strength is 4.6 times 10 to the fourth. And when we multiply that out, we get a force of 0.129 newtons. Not very large at all. So something that is going to be very difficult with this chapter is actually there are a lot of formulas, and they all look really similar. They all use similar letters, so please do your best to keep it straight. Make a formula sheet of your own. That'll help immensely. But for this first problem, it's really going to be the same formula over and over again. So we are going to ignore this sign right here, and I'll explain why here in a second, because I actually got to back up to that previous question. But we basically, to find the force inside of the field, we can multiply the charge that's in the field times the field itself. And that will give us the force. So after we multiply this out, we get 0.428 newtons. Okay, so let's back up. So it did ask for a vector. We want to know which direction this is going. So the field is on the positive axis, and we do get this positive charge going. And if you did your notes on field lines, they flow from a positive to a negative charge. They flow out from a positive. So this is flowing out. And we would then, putting a positive charge in it, it would line up and go in the same direction. So this is going to the right. Whereas this one, this is a negative charge. So if we have a field that's flowing from positive this way, but we have a positive charge, that actually is going to be attracted to the source. So that is going to be a force to the left towards the source of the charge. Okay, and the last one, we can see it is a positive charge, so we know it is going to go to the right. F equals QE. And F is going to equal 4 times 10 to the negative 6 times 4.6 times 10 to the fourth. And we will get a force of 0.8 or 0.184 newtons. Okay, let's go on and see what else we might be able to do here. So suppose 3 microcoulomb. Now, let me get my formulas up here just so we have them handy so we can see what the heck's going on. These are vectors and our field equation. Now, this constant K is the same as for charges is that 8.99 times 10 to the ninth. Okay, so suppose a 3 microcoulomb charge is within an electric field and experiences a force of 0.45 newtons up. What is the magnitude and direction of the field? So that's going to be our F equals QE. And we know our force is 0.45. Our charge is 3.0 times 10 to the negative 6. And we're looking for E. So we'll divide both sides by this 3.0 times 10 to the negative 6. And by the time we put that into our calculator, we will get an E of 15,000 Newton coulombs. Okay, so direction, well, this is a positive charge and the field is going to flow from a positive charge, so up. All right, this question is actually exactly similar to one of the earlier ones, so now would be a good time to practice. So if you want to practice, go ahead and pause right here. I'll put the answers up in a second. Oh, wait. I thought it was identical, but it is not. Okay, so never mind. That's later. My bad. It says, what is the magnitude of the electric field? Okay, so I'm not quite there yet, getting ahead of myself. So let's get the two equations up here. QE and the other one, K QR squared. We haven't used the second one. So what is the magnitude of an electric field produced by a 2.5 microcoulomb point charge? We are considering all our charges to be point charges. So just, note that. Are at the given distances. So we have a distance, right? So this is our R. So we know we're going to have to use the E equation right there. I don't know why I used the capital Q, but it doesn't matter. So we want to know the field, and K is 8.99 times 10 to the ninth. Our Q is, for each of these, 2.5 times 10 to the negative 6, and all divided by our distance, so 0.75 squared. And by the time we type that in, we're going to get 39956 Newton coulombs. All right, and the next one is going to be the same setup. So really, they're all the same. But it is important to know why you're doing what you're doing. So we are looking for the field. We are given a distance. We are given a charge. And that is how we know which formula that we need to know. It's based upon the information that we have. So we are going to know something that happens here. And by the time we put all that in, notice, between these, I doubled the distance, right? And here, notice what happened to the answer if I divide by 4, okay? Basically quadrupled, well, the opposite of quadrupled, divided by a magnitude of 4. Doubled the distance, divided by 4. So what about here? What do we predict? So this is, again, double the distance, right, times 2. So what I think is going to happen here, I think divide by 4. So let's see what happens. So E, K, Q, R squared, E equals 8.99 times 10 to the ninth. Our Q is still 2.5 times 10 to the negative 6. And our R is 3 squared. And we get field strength of 2,497 Newton coulombs. So yes, divided by 4 and worked out. So note that. It's a inverse square law, basically. Okay, so this question right here, that's the one I was thinking about earlier. It is identical to one from before. So go ahead, give it a try, see if you can answer it. And I'll put the answers up in 3, 2, 1. This one. So make sure you are doing these correctly. And there we go. All right, let's go on, see what else we can do with these things. So at what distance does an electric field produced by a charge of negative 11 microcoulombs have? Now, just as to remember about field lines, if we have a positive charge, the field lines are coming out. And if we have a negative charge, the field lines are coming in. And those field lines should be proportional to the strength of the charge. So the field lines are coming in. So what distance does an electric field produced by a negative 11 microcoulomb charge have a magnitude equal to 9.3 times 10 to the 4th Newton coulombs? So we got to remember, as we get further and further out from this field, the force experienced is going to decrease. So that's why we have this formula. And just to know, our other one was Q E. Oops. Q E. There we go. Okay, so we know this is our E, and this is our Q, and we're looking for R. So we have 9.3 times 10 to the 4th. K, 8.99 times 10 to the 9th. Q, I'm going to ignore the negative. Not really concerned with that right now. And R squared. It essentially doesn't matter for this. I would throw a negative into this. I'm not going to have a negative distance. So we'll multiply that out right there. And we'll cross multiply. So we get the R on the other side. And then we'll divide by this boy right here. Positive 4. That was a positive 4. All right, so R squared is going to equal 3.573, which means we'll square root and get R equals 1.89 meters. There we go. Oops, I looked at the wrong set of notes. This is 1.06, and this is 1.09. All right, so you got to jump on the next question. So that's actually the answer to the next question, which is very similar. So if a charge of negative 3.1 microcoulombs produces an electric field, the magnitude 0.78 times 10 to the 4th Newton coulombs. At what distance from the charge? So little grammatical thing right there. So K, Q, R squared. So E, 0.78 times 10 to the 4th Newton coulombs, and 8.99 times 10 to the 9th. And our charge, 3.1 times 10 to the negative 6, all over R squared. Again, we'll cross multiply, and I'll get the R on the left. So basically, I'll get R squared equals 8.99 times 10 to the 9th times 3.1 times 10 to the negative 6. And then we end up dividing by that guy on the left, so 0.78 times 10 to the 4th. And we get r squared is going to equal what I wrote the last time, because I'm looking at the wrong spot. So we square root this, and r equals 1.89 meters. There we go. All right, so that wraps up this section. So good luck on your work.